All right, this is going to be our dilation and scale factor exit ticket lesson 4.10. So what is a dilation? A dilation is a transformation that changes the size but not the shape of the figure. So in previous lessons, we've talked about other transformations as well, like translations, reflections, or rotations. So translations, reflections, and rotations were considered to be rigid transformations. A dilation is not a rigid transformation because it does not preserve the size and the shape. It does, however, preserve the shape. It just doesn't preserve the size. So if you look at the triangles below, while they are both, of course, the same exact shape, one is clearly bigger than the other. So the size has changed. So a dilation is not a rigid transformation or a rigid motion because it changes the size of that object. Pay attention to the notation of the letters as well. We are using prime notation to describe between a preimage and an image. So let's take a look at the two different cases of dilation. You can have what we call a contraction or a reduction versus an expansion or an enlargement. So you can think in simpler terms, right? A contraction or reduction is where it gets smaller, and an enlargement or an expansion is where it gets larger. So you're going to either increase the size of an object or a figure or decrease that figure depending on your scale factor, which we'll address later. Now, the center of dilation is where if we connected all of the points of a preimage to its corresponding point on the image, they intersect at the center of dilation. So I want to show you kind of how that's determined. But for right now, I just want to focus on where the center can be. The center can be on, as in the case here, the preimage. It can be inside of the preimage, or it can be outside of the preimage as well. So these are all the cases where the location of the center of dilation may in fact occur. So take note of the different types of figures that we have there. As an example, the center can change its position based off of what we have. So we're going to see those cases. So let's go ahead and figure out how to find it. How do we find the center of dilation? Well, one way that we can do that is we just need to find the intersection of two segments where the endpoints of those segments, or I should say lines, are going to be the pre-image coordinate and image coordinate. So I guess for me, I'm going to go ahead and focus on t prime and on u prime as my example. I'm going to go ahead and draw an arbitrary segment out here, and then I'm going to go ahead and take that segment, I'll make a copy of it, and I'll paste that here. So for the first segment, I'm going to go ahead and connect t prime and t, as you can see right now. I made sure that it's nice and long as well. Again, it could be a line also. If the segment's long enough, of course, that's fine too. But as long as you have a straight edge connecting t prime and t like I have here, then that's acceptable. Maybe adjust that a little bit. And there we go. And then, of course, the other one is going to be our segment or line that connects u and u prime. And you can see right there that once I have that, that will tell me, in this case, let's change the color to that one to be blue. That'll tell me the location of the center of dilation. So I already now know the center of dilation from just the two. Can I do more? Of course I can do more. I absolutely can draw more. I can draw from V to V prime and W to W prime as well. And they are going to connect as well to that exact location. But in order to find the location of the center of dilation, I only need two. So specifically, I could describe it as the following. I extended segments containing the vertices of the pre-image and image, and I'm going to put in parentheses that's corresponding points. For at least 2 line segments or lines, depending on how you want to extend it out. They intersect at the center of dilation. So that's what I want to point out there. If you have at least 2 of them intersecting, then that intersection is the center of dilation. So that is how we can find it. Now we could draw the others as well if we wanted to. We don't have to do that. You know, you go V to V prime right there, and you can go W to W prime right there. I didn't straighten those out, but I'm just showing you that they would, if I straighten them out, absolutely intersect that exact same location as well. Now, I referenced the scale factor earlier, and I want to talk about that now. The scale factor is the ratio of the length of a side of an image to the length of its corresponding side on the pre-image. So a lot of times I like to write it as the following. So we talk about scale factor. Sometimes we use the letter T as well, which I'll get to that in a moment, as the ratio of an image length to a pre-image length, and specifically the corresponding pre-image length. And this is going to equal the new divided by the old. Sometimes we let that be the letter T, or sometimes you can see it being written as the letter K. It doesn't really matter. What matters is what it does. And here's what it does. If I have a coordinate for the pre-image and I want to transform that by dilating it, all I have to do is multiply that coordinate by the scale factor. Whether I use the letter K or T is irrelevant, because the scale factor is something I multiply my coordinates x and y by. We call that a scalar. Okay, when you multiply the x coordinates and y coordinates by a number, it's a scalar multiplier. So we're multiplying them in order to come up with our new coordinates for our image. That's what I want you to take away from this. You can actually determine the coordinates of your image by multiplying the coordinates of your pre-image by the scale factor. How do we find the scale factor? It's the ratio of the new over the old. An image length divided by its corresponding pre-image length. That's what scale factor is. So a couple rules about scale factor. If you have a scale factor that is less than 1 and also can be negative, it is a contraction or a reduction. Remember that this means that it is going to shrink versus it's going to get larger as opposed to shrinking if it's an enlargement or an expansion. Now, another way that you can phrase this is if the absolute value of the scale factor is less than 1, you have a reduction or contraction. So if you looked at the absolute value of negative 5/8, that is less than 1. Just as 1/4, absolute value of 1/4 is less than 1. Those are examples of where it's less than 1. The reason why you have to say that, or the reason I'm saying that, is because if you look at the enlargement cases, for the enlargement cases, you can be whole numbers or improper fractions, and they also can be negative, right? Just as with reduction, you can have factors less than 1 and can be negative as well. But the reason why it's important that I mention the absolute value is because if you look at the absolute value of a scale factor and it happens to be greater than 1, it's an enlargement. So a common mistake is that when people see a number like -5, they think, oh, that's the scale factor ratio? That's the ratio which is the scale factor? That must be a reduction. No, actually it's an enlargement because the absolute value of -5 is greater than 1. And also improper fractions as well. The absolute value of -8/3, that's actually larger than 1. those numbers are further away from 0 than 1 is. So they are, in fact, going to produce expansions. And if the number is closer to 0 than 1, then it's a contraction. The negative indicates the following. It indicates a 180-degree rotation about the center of dilation. That's what that indicates. So if you have a negative scale factor, or in this case you have a negative ratio, it indicates that another transformation actually has occurred. And we get to explore that a little bit later in more detail. For right now, we just identify that as a rotation as opposed to just saying that it's an enlargement or a reduction. So in this example here, anytime you see these QR codes, just pause the video yourself and try it out. Maybe take a moment to do that. You should have selected C3 as an answer. In this particular case, C3 is right here. Right away, I can tell if I connect U and U prime. It's not perfect. It's not as straight as I may have liked it, but it connects the two, which is exactly what we said it should do, right? And V prime also connect that way. Again, it's not 100% perfect, but it does connect. Now, I bring that up because they intersect each other at C3. However, they also told us in the problem that the scale factor was -2. So one of the little rules that we have to follow here is that -2 signifies two things. One, it signifies that it is an enlargement or expansion. I'm going to use the actual vocabulary because I want you to become used to using that. Why is it an enlargement or an expansion? The reason is because the absolute value of -2 is greater than 1, so therefore it's further away from 0 than 1, so it has to be an expansion. The other thing that it signifies is 180-degree rotation about the center of dilation. And in our case, that would be C3. That is also happening as well. Okay, so you can see in the diagram right there, 180-degree rotation is happening. And actually, I mentioned earlier, this is actually why two transformations are happening. If you take this segment momentarily, I'm kind of highlighting it here. I'm going to go ahead and kind of copy the segment piece, and then I'm going to kind of manipulate it a little bit. Actually, I don't even need to copy it. So it's not only just making it larger, which it does, but notice how U prime is on the other side of where U would be located. So it's actually rotating it 180 degrees about the center of dilation, and then it's also increasing it as well, like I'm showing. Okay, through an enlargement, like that. So it did two transformations in one. That's what the -2 represents. So if you're looking at 1/8 as an example, that is less than 1. That is a contraction. -3.5's absolute value is greater than 1. That's an expansion. 0.6 is less than 1. Its absolute value is less than 1. It's a contraction. And the absolute value of 5 is greater than 1. That's an expansion. So we should also be able to identify whether a scale factor shows an expansion or a contraction. How far away is the number from 0? Is it further away from 0 than 1, or is it closer to 0 than 1? If it's closer to 0 than 1 is, then it is going to be a contraction. If it's further away from 0 than 1, it's going to be an expansion. You can also use ratios as well to identify whether it's an enlargement or a contraction. So if you look at this example here, we want to notice very quickly that it's an enlargement because it's taking the new divided by the old. 6 divided by 2 is 3. 3 is greater than 1. Therefore, that's an enlargement. And it does indeed make this segment longer. 3 times as long, in fact. Over here, I have a trapezoid, and what I notice right away is I see a contraction or a reduction. You can use both words or one or the other, doesn't matter. But I also see a 180-degree rotation as well. In this case, about the center. I'm just going to call it the center for now because we're going to explore that later in a future chapter. I don't necessarily care what the center is right now. I'm just telling you that there's a 180-degree rotation. I know that because we have a negative scale factor. It's also a reduction because the absolute value of negative 1/2, of course, is less than 1. So it is a reduction. And I would point out that you can even see how they took our coordinates here for A as an example, and they multiplied it by the scale factor. Now, when they do that, we can write it like this, I suppose. That is going to give us A prime, which ends up being -1, -1. So there is another case right there again where you can find the new coordinates of your image from your pre-image coordinates by multiplying it by your scale factor. So this slide right here directly demonstrates what I was saying right here. That is the point I'm trying to get at, okay? Now, that being the case, that's what you want to notice. If you have a positive scale factor and it's greater than 1, of course, that's an enlargement. If it's a negative scale factor, like it is there, that's going to be a reduction, and it's going to be, well, it's a 180-degree rotation if it's negative, but it's a reduction because it happens to be less than 1. So in my case here, one way I can find the scale factor is by comparing the lengths of the new to the old. So this is new and this is old, and they did 4/2. So the length of 4 divided by its corresponding pre-image length, that gives me the scale factor as well. Now I notice that C is the center of dilation there, and it is not between Q prime and Q. If it's not between them, it's a positive scale factor, as is the case here. You can also look at coordinates as well, Q prime and Q. Q prime is 2, 2. Q is 1, 1. And just look at the ratio of the x and y values. The ratio of the x values is 2/1. The ratio of the y values is 2/1. That reveals the scale factor as well. Okay, so just keep in mind that there's more than one way to find the scale factor in the coordinate plane. So how would I find the scale factor here? Pause and determine for yourself. One simple way, again, could be comparing a side length that's new divided by its corresponding old side length. So here I have a length of 6 divided by a length of 3. So that gets me 2. So my scale factor would be 2. The best answer here is going to be 2. I would maybe reference this as an exit ticket help slide. In this example here, I have to figure out this factor of dilation. I'm not in the coordinate plane, but I do have the lengths of x prime, z prime, which is this length, and this length. So x prime, z prime, I have x prime, z prime divided by xz. That's going to equal 40 divided by 16. Which reduces to 5/2. And that is going to equal 2.5. 2.5, of course, the absolute value of 2.5 is greater than 1, so this is going to be an enlargement. You can also call it an expansion. Okay, and I've just calculated that by comparing the length of the image to the pre-image length. So you can pause the video and see if you can come up with the scale factor here. You should have selected 3. So in this particular case, if we compare the new to the old, we have a prime b prime divided by ab. That's the new over the old. In this case, we would end up with 3 over 2 divided by 1 over 2. 3 over 2 divided by 1 over 2 is the same thing as 3 over 2 times 2 over 1. Because you have to multiply by the reciprocal. You're dividing by a fraction. So that means that simplifies by canceling out, and we get 3. So the scale factor will be a 3 over 1, or 3. Again, that's an enlargement. Now, pay attention to the fact that they're on the same side of C. C is not between them, so I know the scale factor has to be positive because of that. There's no 180-degree rotation happening here whatsoever. So looking at your exit ticket for the final part of this video, several of these questions are outlined. We just did one exactly like this, so I would refer to the slides for these two specifically. I would encourage you to look back on the completed slides provided by your teacher as well as this video. And then for this one, just keep in mind what I talked about earlier. Notice how C is between the two, the pre-image and image. What did I say you have to consider when you have C, when the center lies between them? What is actually happening there? The hint is that there's a rotation happening there. So if there's a rotation happening there, that'll tell you the sign of your scale factor. And the only other thing I want you to keep in mind is, remember, scale factor is new divided by old. Okay? All right, that is going to represent our lesson over dilation and scale factor for 4.10.